Okay, today we're going to talk about exploring polynomial functions. When we talk about exploring, we're talking about like the main characteristics or what we see when we look at a polynomial function. We're going to talk about key elements of the graph. We're going to talk about domain and range, which you already know, and we're going to talk about relative and absolute maximum minimums. So you're familiar with a maximum minimum. We just kind of dig a little deeper into what type of maximum minimum we're looking at. So a relative maximum minimum is the highest or lowest. So max would be the highest, min would be the lowest point in a particular section of the graph. So if you're not looking at the whole picture, it's what part of it that you're looking at. So in a particular section, so like this graph down here, the relative maximum minimum will be the maximum minimum, the lowest or highest point that we can see in this graph. Absolute maximum minimum are the highest or lowest part of the whole entire graph. So highest or lowest, depending on if you're talking about maximum or minimum. Okay, so looking at a relative maximum. A relative maximum, if looking at this window, relative is what you can see. So the highest point that we can see that actually makes a high point would be right here. So this is our relative maximum. That's the highest point that we can see. So in this case, we're going to say that's at about a half, right? So at y equals 0.5, right? Relative maximum. The point itself, you could say it would be at 1.5 if you're talking the exact point. But the highest part that we can see, because this of course goes on forever, is right there at that about 1/2. Okay? Relative minimum, the lowest point that we can see is right here, which would be at, or I guess the relative minimum would be right here. We're going to say max. This would be our relative min. That's the, not the absolute lowest, but that's the lowest point besides the absolute lowest. So that's the relative minimum, and so we're going to say that's at f of x equals 0, or at the point about 1, 0. So you can write it either way. You can write it as a point, or you can write the lowest value that you get is 0. Okay? Then, in this case, our absolute maximum, right, would be somewhere up in this area. Our absolute maximum we can't see on the graph because these both approach infinity, right? So it's going to be infinity because it's going on forever and ever up. So absolutely maximum, it's going way up over here. Absolute maximum is going way up over here. So we're going to say f of x equals infinity. And we're probably going to kind of keep it that way because you can't really get to the actual point itself. So we're not going to write what the point would be. Absolute minimum, the absolute lowest point on this graph that we can see is right here, the lowest point period, at about 1.5. So we're going to say f of x equals 1.5. In this case, we know it's about 2.75, 1.5 is the actual point if you're looking into the points. So let's talk domain. We talked domain before. Domain is your x values. So it's the values of x's that the graph can touch. This graph goes left forever, right? Because even though it's going up, it's still going left. And this graph goes right forever. Even though it's going up, it's going right. So our x values cover from negative infinity to infinity. Range, remember, is our y values. So range is y values, which goes up and down. So we're going from, our lowest point is right here at about 1.5, right? So from 1.5, and then we're going up infinitely. So we're going from here, and the graph goes up forever. So we're going to say it's from 1.5 to infinity. Let's make this a bracket because we're including that 1.5. Okay. So we talked about intervals of increase before and decrease. Increase is when you put your pencil on your graph and you're going up. So we're going up from here to here, right? So from 1 to about 1.5. And then also from, we go down from about 2.75 to infinity. We always link them with the union because that's two parts that we're going to pull together. So intervals of decreasing, we're decreasing from negative infinity, somewhere way, I mean it can be far, far away, from negative infinity to 1. And then also we're decreasing from 1.5 to 2.75. And remember, increase and decrease is just when you put your pencil on your graph, up is increase, down is decrease. So increase, decrease, increase. Decrease, increase, decrease, increase. So just write the intervals, the x values. So from here to here is decrease, from here to infinity is increase, from here to here is increase, and then from negative infinity to here is decrease. It's the turning points. Okay? So let's look at a real life example of when to use this kind of stuff. It says, you are drawing a rectangle with side lengths of x minus 5 and x plus 3. A polynomial function that represents the area of the rectangle. So area of a rectangle is your length times your width, right? So area is length times width. Well, we know the area of the function equals length 5 minus x times the width, x plus 3. Okay, so that's your function right there. That's your polynomial function. Area given x equals 5 minus x times x plus 3. So I went ahead and graphed it over here. I did my graph by 2, so negative 2, so that would be at negative 3. That's at positive 5, and then my height here. When you graph it, what value maximizes your area? We know the graph is symmetric, right? So halfway between negative 3 and positive 5 would be positive 1, right? Positive 1 coincides with 16. So the area will be at its maximum, which is right here, at x equals 1 units, whatever units we're using here. It could be feet, could be meters, whatever. What is the maximum area of the triangle? So x is your value that you plug into your sides. This is your area. Y equals your area. So the highest area that you can get is 16. We'll do y equals 16 units. And of course it's area, so they're going to be units squared, right? So 16 is your maximum. So we learned in the past years that if you can find your maximum in the calculator by going to second calc maximum, left bound, right bound, that kind of stuff. So we're using the same concept there, and we're going to find that 1/16 would be your maximum over here. 1 is the value of x, 16 is the value of y, which is your area. So that's how those come about. So what is a reasonable domain? Well, if you look, a reasonable domain is what makes sense in the context. Well, y is your area, right? Area is always positive. Area has to be positive, right? We have to have a positive number for our area. So really a reasonable domain would be from here to here, because these values keep everything up in this area, right? Keeps it positive. So a reasonable area or domain would be, sorry, I skipped one. Reasonable domain would be from -3 to +5. And we're not including those because we don't really want an area of 0, right? So we're going to go anything above this, anything above this. So anywhere in here, okay, makes our positive. Down here doesn't make sense because we don't want a negative area. Y is negative down here. Y is our area. So what is the domain? The actual overall domain goes from -infinity to +infinity because this goes on forever and this goes on forever. So we're going left and right infinitely. Okay, so and this is because we want to keep y positive because we don't have negative area, right? So looking at our graph a little bit more, what is the interval increasing? We're increasing from way down here, -infinity, up to 1, right? At 1 is our turnaround point here. So we're increasing from -infinity to 1. And this means as x gets close to 1, y increases. So as x gets close to 1, y is going up, okay? And then the last question down here, and I'm going to scoot my paper down for a second. What is the interval decreasing? So we're decreasing from that turning point, from here down, right? So we're going from 1, but we're actually going toward, even though we're going down, we're going in the positive direction. We're talking our x values. So we're going in a positive x direction. So we're going from 1 to infinity. And this is as x gets greater than 1, y decreases. So y gets smaller, which is our area. So as our x value gets close to 1, our area increases. As our x value gets greater than 1, our area decreases. Okay? So let's flip it over on the back. So example number 1. All right, so we have a piece of paper here. It's a 22 by 12 piece of paper. Okay? We're looking to cut the corners out and fold it to make a box. Okay? So if we do that, if we have a height of 0, so if we don't cut the box yet, right, we have a 12 by 22 piece of paper. So this is going to be, the length is 12, or we'll do 22. Length is 22. Width is 12. And how do you find your volume? Volume of a rectangle is length times width times height. So 0 times 22 times 12 would be 0. Remember, it's going to be in inches cubed. Okay? If we have a height of 1, so if this is, these are 1 by 1s that we're cutting out to make it fold up to a height of 1, that's going to drop 1 down on both sides of this. So instead of 22, it's going to be 20. And we're also going to drop 1 down on each side of this. So instead of 12, it's going to be 10. So 1 times 20 times 10 would be 200 inches cubed. Okay? So again, if we make the height 2, that means we're going to cut 2 from each side. So 2 from here, 2 from here, 2 from here, 2 from here. So instead of being 20 now, we're going to be 18. and instead of being 10, we're going to be 8. So 2 times 8 times 18 gives us our new volume, which is 288. Okay, so looking at number 3, or height of 3, that means we're going to take 3 inches from each side, so really 6 from each side in general, because 3 from this part of it and 3 from this part of it, so 6 from, this way, 6 from 22 would give us 16, 6 from 12 would give us 6, so 3 times 16 times 6 gives us our new volume of 288 inches cubed, right? And then we're going to run back down, so we're going to do 4 from each side of 22, so it's 8 in total is coming out of 22, and that'll give us, let's see, 4, 6, 18, back down would be, take 2 more, 14, take 2 more, so you can see we're dropping down by 2 each time. So we would have 4 times 14 times 4, and that would give us 224. And then any x, right? So we're going to take, see how we took 2 from here, we took a total of 4 from here, we took a total of 6 from here, and we took a total of 8 from here. We're doubling what our height is because we have to take it from both sides of it. Does that make sense? So our x factor would then be 22 minus 2x. And same thing here, we're taking 2 more each time. So we're taking 2 from here, 4 from here, 6 from here, and 8 from here from the original. So that would be 12 minus 2x. So to find our volume, we would have x times 22 minus 2x times 12 minus 2x. And that would be our volume. So it says write an equation in factored form to represent the volume of a box given x height in inches, which would be here. So this would be x times 22 minus 2x times 12 minus 2x. So there is our factored form of our equation. Okay, so I went ahead and sketched my graph over here. It says graph the equation in your calculator, sketch the graph below using the window given, change this in your calculator using the window button. So if you look at your calculator, you can change the window button. So I went right here and changed the window to match an x min of -10, max of 10, a scale of 1, a y min of -20, a y max. I put 300 in there, and then a y scale of 1. So when I put that in, I went ahead, this was at 0, 0, my other was at 6, 0, and then my maximum was at 2.4, 297.5. So this is the maximum volume right here, because y is our volume when x is 2.4. So if you plug 2.4 in here, that gives you your maximum of almost 300. All right, so using the information from the equation, estimate the height x that will give the maximum value y. So that's how we can find it right on our graph. So we say the maximum value of 2.4, which is our x, gives us a maximum value of 297.5 as our y. Okay, what is the reasonable domain from this function? Again, reasonable domain, we want our volume to be positive, right? We want it to be above the line. So our reasonable domain goes from 0 to 6, right? And we don't want to include them because we don't want it to be 0. So our reasonable domain is just between here where we get, like we can get 1 wherever this lands, 2 wherever this lands, 3, you know, and so on. So we want to make sure that we're getting positive numbers. All right, example 2, Write an equation in factored form to represent the volume of a rectangular box formed from a 9-inch by 12-inch piece of paper given x depths in inches. Again, same thing. We start with x. That's our height. Our width is 9 minus 2x. Our height is, or our length is 12 minus 2x. Remember, we have to go down 2 each time because you take 1 from each corner. So if I have to take 1 from this corner and this corner, so I would take 2 in total from that whole side. Okay? Graph the equation in your calculator using information from the equation. Estimate the depth x that will give you the maximum y. So if I go graph this in my calculator, here's my calculator, and I say y equals x, and you guys can all type this in, 9 minus 2x, 12 minus 2x, and then graph. Our graph is looking like this, so we don't need it as tall, but our maximum height, we're looking at the relative maximum, not the absolute maximum. So our maximum height here, so if we go to second trace, we're looking at the maximum. Left of that maximum is about here. Right is about here. And so it's going to be at 1.681.87. So 1.681.87. So there's our maximum value. And then they say, what is the reasonable domain? So if I look at this, my domain goes from here to about here. Remember, we want to keep it positive, so we want it to be above the line. We don't want it to go down in this area. So we're going to say from 0 to about 4.5 would be our reasonable domain. So from 0 to about 4.5. So, and this up here again tells us that a height of 1.6, or I guess it's 1.7 really if you round appropriately, gives us our maximum volume of 81.9. Okay, so that's what that tells us. That's the meaning of it. So we're looking for the interval which makes it positive. So you want to make sure it's positive the whole time. So this keeps the volume positive. All right, so you've got some practice problems down here. It's 3 questions. I want you to take the rest of the class time to try to finish those up, draw them out, figure it out, use your calculator. If you have questions, please let me know while I'm in the classroom. Thank you, guys.